seminar, which is an overview of, well, a sense of about 10 years worth of work on taking superconducting devices from things which, well, barely show quantum coherence effects to showing them very dramatically. And then I'll move on to some thoughts about, well, where this might take us further into the future. Now, this is an outline that I'll cover as part of the regular seminar. But I understand that Andy Kent's quantum physics class is here. Can I get a show of hands? There they are. Wow. Okay. So I can further. It had been further suggested to me that on account of the special guests coming to the talk, that I actually give you sort of a little bit before this, which I will indeed, of what's the whole point of why are we interested in doing this stuff? Because I tend to, when I tend to speak to quote experts or older people like myself, I tend to assume they know all this because they were all around in the 1990s and knew all the big stuff that was going on then. But you guys were, you were in nursery school or something in the 1990s, so I shouldn't assume that they taught that at the Garden Center nursery school or something. But I'll get to that in a moment. But I will indeed give a lecture which is about Josephson Junction devices. So I'll have to talk a little bit about what the basic physics of that is, which is basic mechanics, in fact, and then some history of a series of experiments conducted beginning in the late 1990s, which brought us to sort of a qualitatively different point about the functioning of these kinds of electronic devices. And as I said, in the later part of the talk, I'll discuss how this work has been mostly about single device experiments, and we think the time is right for going on to multiple device, multi-qubit structures, and so there's actually issues of what is an architecture that you should shoot for, and I'll discuss that. Okay, but I'm going to, in fact, jump to some other stuff. Let's see if I can do this on the fly here. And I'm actually going to mostly use the blackboard for this. But first I want to move to a few statements that I have, which are like slide 80 of all of these slides. So you're getting to see some stuff that I don't show very often. So, well, when I talk about quantum information or quantum computing, I have to make a choice. So I'm going to restrict this to maybe 10 minutes. So this is going to be a really whirlwind thing, especially since the subject that I'll be talking about comprises inputs from these three extremely distinct subjects, from quantum physics, from the theory of computing, and also from the subject of coding and communications. So I can't do that in 10 minutes. What I will do, though, is give you a few thoughts about why sort of the basics of digital computing got rethought over the last, 50 years, let's say, with a few important milestones that made it mix together with quantum mechanics in a quite unexpected way in the 1990s, in fact. So here's a slide which just reminds you about some basic things about computing. So you probably know that if you want to make a computing device, you want to implement logic operations, and that you can do it with this set alone, these Boolean logic operations. Let me concentrate on the and. It's a theorem that if you have and not, actually if you have them together and have an and, then that's actually enough to perform all computation, anything that a digital computer can do. It can do, if you compile it down to these elementary things, it can do it with only that. So now I'm going to actually transit to the board just to make a few remarks. And could I have the assistants to get the board, get the screen up? And I guess I have an even more challenging task of getting the, this will do.
push B, I think, on your computer.
Was there a question?
No, I was just going to say you want that black, so push B on your computer.
If you type the B key, then the screen will go, then the light will go off.
Oh, well, but, okay, I may as well have a spotlight on the board,
Fine.
so. Okay, now, of course, I need some chalk. Now, that's, it's a little low here. Oh, here it is. Now I see some. Okay, I can do it. I can Here's a NAND gate. It has the property that.
So the spotlight is bad.
Okay, so tell me tell it your Mac trick. If I type G, does it go green or something? I don't know. Okay, so as I said, is this, the glare is okay now? Yeah. So NAND gate. You know what that means. It basically means that if you have 2 bits, I'll call them A and B, the output is A times B. Just zeros and ones. Now, it was observed, so a little story about, for a moment, about energy dissipation, about energy consumption in computation, because this is a very interesting story in and of itself. But it was recognized, and I'll write the name Landauer. There's something which is called Landauer's principle. This is an irreversible step. In other words, that you can't, given the output, you can't know what the inputs were. And this irreversibility was recognized as something which Landauer wrote down some simple analysis that said that, therefore, there's a certain minimum energy cost that you'll produce heat, and the amount of heat you'll produce every time you physically run an AND gate is this famous formula KT natural logarithm of 2. So there's just one little fact for you that everybody should know anyway. That,
you have A plus B or A times.
this is times.
Time.
That's an AND,
That's
an AND gate, not an NAND gate.
Oh, sorry. Yeah.
I'll be
I
like my
didn't
students
write.
correcting
I
me.
didn't put symbols. Okay, thank you for the debugging. Yeah, I wasn't doing an AND gate, so that's right. And so it was thought, this was back in the 1960s, that therefore there really is a lower limit on the amount of energy consumption that computing, would consume. But it was understood. So there was in fact a breakthrough in this, which has yet to have significant consequences, except maybe it has had big consequences in understanding the sort of quantum story of computing. That there's another gate, and I'll draw a symbol for it, something called the TwoLevel gate. And it's a 3-input, 3-output gate, ABC. So there are 3 bits in and 3 bits out. The upper 2 bits are just passed through without change. And the final bit has this AND embedded in it, A times B, but then also plus C. And you do all this modulo 2 arithmetic. So that's the TwoLevel gate. And it is, in fact, reversible. If I give you the input, you can know what the output is. Therefore, the Landauer analysis doesn't apply to it. And it was actually Bennett, Charles Bennett, who, with this and related reasoning, established that, in fact, there isn't a lower limit to energy consumption in computation. That there's a way of doing everything you thought you needed to do with this, you can do with that. You may say, don't you have a giant proliferation of extra bits? But he indicated sort of garbage collection techniques of getting rid of the sort of extra work bits that you have accumulated. So he established that in the 1970s, that this was true, that in fact computing can be reversible. Now, it was further observed that because computing could be reversible, it could be done in a quantum way. Now, let me explain what is meant by that specifically in this picture. The A is meant to be something which can be a 0 or 1, and B and C as well. So let's adopt our favorite quantum two-level system. Let's say spins. Andy, have you covered spin yet?
Fortunately, that's next week.
Haven't gotten there.
Yes.
Okay, well, you know, so this
Something
is,
about two-level systems they
Yes.
had a test on.
so take your favorite two-level system, I mean a double well potential or something like that. And let's say we'll use that as the physical embodiment of this 0 and 1. I think I'll do it with spin anyway to
Yeah,
anticipate or get them all boned up
Yes.
for next week. So so it means that these three inputs will be three spinning particles, and this may be spin up, and this may be spin down, and this may be spin down, and that will stand for 1, 0, 0. And then you imagine or you consider what happens when you push this through the Toffoli gate. As it happens, it leaves them unchanged. If you use the truth table of the Toffoli gate. So it was noted that okay, I can announce this, but what does that imply for what happens here? This you consider as something that happens as time evolves. As at early time, the state is this. You have a period of time which is the Toffoli is happening, and then you have a final state. And the observation that this is reversible tells you that there is in fact some quantum evolution, some Schrödinger equation basically. There is some, in other words, Hamiltonian. That will enact the Toffoli. So that was the observation. Now we've gotten up to more or less Feynman, and also, well, Benioff really also observed this, except, well, you've never heard of Benioff, maybe you've heard of Feynman. So in the 1980s, it was noted that because digital computing could be reversible, it could also be enacted as a quantum process. And that so far was all up to this stage of this discussion. That is, it was noted that these quantum evolutions, evolutions dictated by the Schrödinger equation, could emulate regular digital computing. But then it was asked, the following was asked. So this, let me just draw a little quantum diagram. So this is, when you talk about up and down, or spin up and spin down, there are two energy levels, say, of some particle or atom or something like that. Let me use quantum symbolism for them. This you're in this state, this upper energy state, it's spin up. You're in this lower energy state, it's spin down. But quantum mechanics says that you're also allowed to make quantum wave functions which are superpositions. Let's say that superposition of the ground state and the excited state. So perfectly fine as a piece of quantum physics. But now we're outside the rules of Boolean logic. We don't have zeros and ones anymore. We have objects which are wave functions which have zeros and ones in them. So it was recognized, and now we're up to, this was sort of 1980. In 1985, someone by the name of Deutsch, in 85, he said, well, why shouldn't we do that? That extends the rules. Now we have a new formal system, not Boolean logic anymore, but some other kind of logic, where you commit, kind of regular gate operations, but superpositions as well. And then, actually, now I can probably do this with my. Yeah, let me go back to the. So that ends the sort of brief history of reversible computing, therefore a quantum realization of computing, and therefore, well, maybe we could permit superposition. Now you can,
Does anyone have any stupid question about this?
yes.
So what's the connection between the computing being reversible and the computing being done in a quantum mechanical way?
Oh, well, it's related to things that you'll learn probably, which has to do with if a wave function is evolving under the Schrodinger equation, it evolves in a quote unitary way. That means that if two states, that means that the probability vector is conserved. If you put in a properly normalized wave function, it remains normalized. But it also means that if you have two orthogonal wave functions and you have them evolving, that they remain orthogonal at the end. And so it means, in short, that you can tell the input from the output. And so it shares that property. I mean, this reversibility is a subset of that property, in fact. Now, the writing of the Hamiltonian for the thing that's now been hidden is actually quite complicated. I mean, in a sense, that's the subject of what I'm talking about in my seminar today, which is, how do you actually get in the laboratory, how do you actually get these things to happen? And that's been, the really hard story for years and years. Okay, now I need my Apple help with how do I unblack this thing?
Oh, there's no way to do that, sorry.
Yeah.
It's irreversible.
I use a chalk for the rest of the hour.
Hit B again.
Hit B again.
B again, okay.
What did you hit there?
Yeah, okay, great. So there we have these things. Let's, so this is what was discovered in, this is not so well documented. So in 1994, another scientist, with knowing all this, but having this as a puzzle in his mind, saying, well, I have these new rules of computation, what can I do with it? And he found a spectacularly important thing to do within these rules. So this is a sort of sketch of what he discovered. So he discovered an algorithm using these rules for what's called period finding. And I have all sorts of eavesdroppers and blah, blah, blah. It's the problem of finding prime factors. You're given some integer n, 15, and you're having your computer tell you what its prime factors are, 3 times 5. Except you want them to be 1,000-digit numbers or something, and then you can crack codes if you can actually do that. And what he found was that there's a circuit that he can write, which would be hard for me to write in this box, but I can assure you it consists only of Toffoli gates. And it does some specific arithmetic operations. And it has inputs of this form that I just mentioned. So the inputs are not zeros or ones. There's these superpositions of zeros and ones. And then finally you have to make measurements. Now I guess I should have said you can, well, it depends on how you state the rules, but you could say you can have rules where you not measure a bit to determine whether it's 0 or 1, but you can actually make a measurement to determine whether it's 0 plus 1. I mean, I'm gesturing this way. If there's spins, it actually just depends on the direction of the magnetic field of the analyzer. If the magnetic field is pointed this way, then you distinguish up from down. But if the magnetic field, or the magnetic field gradient of the Stern-Gerlach apparatus is pointed this way, then you distinguish whether it's 0 plus 1 or not. And you need that style of measurement as well. So you need a little bit of a change of rules of what measurements you do to extract information. But then what Shor found was that there is indeed a procedure of this form, and it's very, very, very compact compared with any known regular Boolean logic implementation for solving the same problem. I have one little further detail. There's actually quite a variety of ways in which you can set up Shor's algorithm. This is how many bits it takes and how much time it takes. The important thing is it takes no worse than polynomial time in the number of digits of the problem, whereas any known classical method for doing this, Boolean logic method, this scaling is exponential. Notice it's even better than that. There are ways of making it extremely parallel so that the time, the duration of computation only scales logarithmically, so it's really super fast if you permit more bits, more working bits of the calculation. Okay, so that's what happened in my, I was sort of in middle age, working along in solid state physics, and this big bomb went off, which made it clear to a lot of us, a lot of people working at that time, that this was a really important problem of how you turn this knowledge, this fact, into practice. So now I'm finished. So okay, students, you've gotten your dose of the stuff that I don't normally tell in my seminars, and now I'll bury you with superconducting gizmos, because it was recognized that, well, in fact, this is kind of laboratory agnostic in the sense that it doesn't have to be with superconducting devices. It can be with anything that has zeros and ones. So that's atomic physics, it's nuclear spin physics, it's the physics of photons, photons being this way or that way is another 0 or 1. So there was or there is, even still going on today, a kind of long period of assessment of which things could actually manage to do the tricks that are required to run, let's say, Shor's algorithm, or other algorithms that are facilitated by these new rules. But today I'll talk about superconducting devices, so a particular branch of solid-state device physics, and first give you a sense of the basic physics of these things, and then go on. I already told you this outline. So, basic physics. So, actually it started, well, the connection, so to speak, between these kind of devices and quantum bits sort of started in the year 1985, although not really, because nobody, in fact, was talking about qubits at that time. But it was just the question, could you see energy level structure? Could you see basic quantum physics behavior in an electric device with superconducting structures? And this already set up kind of a puzzle, which remains with us to this day, that you would think, we're invoking quantum physics, and I'm talking like spin up and spin down. So you think all of this has to be happening at the atomic level. But of course, quantum physics applies, not simply, but it applies to everything. So if you can get a phenomenon to work quantum mechanically, at some larger scale, and if I, run this story up to the present, we now have, perfectly good Schrödinger equations where the scale of the object is this, as I can gesture with my hand, centimeter sizes. But that's okay, but it means big challenges for the experimentalists that you don't let enough noise into the system basically for classical physics to take over. So the efforts of this group at Berkeley was to show that a modest size, sort of micron scale size electric circuit, and I'll show you some picture of it in a moment, is actually capable of showing quantum structure. And even though at the outset it looks very classical, that is, there is indeed some wires, there's some evaporated metal structures with which you make, well, a capacitor, regular parallel plate capacitor with dielectric. You make another thing, which I'll give you several interpretations of, which is in fact a tunneling structure. That is, you have some metal. I'm actually going to say this in a few minutes, so I'll say it here. You have a piece of metal, simple metal, aluminum, niobium. You oxidize it, and you grow on top of it some other metal, so that forms a contact where superconducting Cooper pairs can tunnel through. But it, in fact, from a point of view of electrical scientists, it's a kind of inductor, basically. That is, that it's something which relates current to, I'll say flux, but in a nonlinear way. So this group at Berkeley was exploring these things, and I'll explain somewhat as the as the lecture goes on, that this structure, including the things with its current sources and voltage probes and things, can be described by mechanics, lossless mechanics, reversible mechanics, if you will, and therefore you can write a Hamiltonian and a Schrödinger equation for this. Now you have to check whether it's perfectly fine. I mean, balls rolling down ramps or something also have Hamiltonians, but we don't usually say that they have all the attributes of a Schrödinger equation. This has to do with so-called quantum coherence. But anyway, the potential of the rolling ball, so to speak, has some shape which is locally like this. And if you just suspend disbelief for a while and you just say, let's solve the Schrödinger equation for this structure, it turns out the scale of things is such that the energy spacings are not that small, so it's not very classical, and there are only a few energy levels predicted in this metastable well produced by the dynamics of this. And furthermore, the shape of that well is tunable by changing some classical parameter, which is in fact current bias in this case. And furthermore, you can apply radiation to this system in the form of microwave signals. And so you can look for a kind of usual thing, which is just a resonant effect where you have the frequency of the radiation in resonance with transitions in this few-level system. And so this was the first experiment where you really saw some structure, where you saw structure that corresponded, not very dramatically, it had to be admitted, so this was a kind of spectroscopy of this, or claimed spectroscopy of this sort of molecular potential system. Now, as I said, this was not very promising in the sense that, well, this data is very noisy, it has very broad lines, and it is implausible, in fact, with this data that you would actually expect to be able to make these coherent superpositions of 0 and 1. These superpositions are quite delicate things. They're disturbed by noise. They're disturbed by perturbations. So, but at least this said that, you know, some quantum phenomenon was emerging. But the story gets much better, in fact. Let me spend a few minutes talking about this structure. So here's, you know, symbolically this Josephson Junction. I already told you what the metallurgy of it, you know, what physical structure you make. It's a structure which has a current voltage characteristic. So it's a two-terminal device from the point of view of an electrical scientist, and it has a current voltage characteristic, but it has two branches of that characteristic. One branch is this, which is sort of a regular resistor, but with some nonlinearity, which is characteristic of tunneling. That it takes, you know, takes a certain amount of voltage to sort of overcome a barrier before the current really goes up very much. But then it has another branch of its characteristic. Because these are superconductors, it has a characteristic where current can flow in the absence of any applied voltage. Depending on the conditions, any amount of current can flow between plus or minus some characteristic maximum, so-called the critical current of this junction. Other arguments provided by Josephson, for which he got the Nobel Prize, showed that this the amount of current indeed is not controlled by any voltage, but it's controlled by a time integral of the voltage. This is Josephson's law, or one integral of Josephson's law, that there's another parameter which can be referred to as a phase or a flux, which is electrically characterized by the fact that it's a time integral of the voltage. This was, Anderson and Rouse actually saw this feature within a couple of years of Josephson's prediction of it. Oh yeah, another historical comment. When I first came to IBM Research 30 years ago, approximately, there was a big department which was in the process of being shut down, dozens of engineers. And the goal of this department had in fact been to make a superconducting digital computer, which was the so-called Josephson Project. As I said, they had just decided early 1980s that this was not going to work. And so this some of you, or some of the older members of the audience remember this, and this can worry you that, well, we're going to again go down that path. And so I like to, or the point I like to make is that the concept was in fact to use the two-branched nature of this, and so that the zero would be this zero voltage state, but the one was this regular kind of resistor state. So it was very much not a dissipationless computer. It was not at all a quantum computer. And it was judged to, so it had to be judged by the standards of regular digital computing, and it was judged that CMOS devices were coming along pretty fast. And in retrospect, that was really true. So don't give up. One point I'll make is that for any discussion I'll have today about quantum computers, we stay strictly on this branch where, you know, reversibility is sort of possible, and quantum coherence is at least in principle possible, but not in evidence yet, at least in anything that I showed you so far. Now, maybe I'll skip this. You know, workers got intrigued by this question: could we indeed have a quantum coherent device? And it was Nakamura who saw that there was indeed a hint of coherence. That he set up one of these Schrödinger equations, which had two energy levels and had a knob that he could tune that would bring them into coincidence. In other words, would bring them to the same energy. But then quantum tunneling would split those energy levels. And he could run a little protocol, you know, switching this parameter, which was actually a gate charge, back and forth, and look for whether he could produce, or this group at NEC, could produce coherence. And they saw some sign of it. This already just, you know, gives a little hint that coherence is related with sort of wave nature of these, well, not particles, but states. That is, that they exist in superpositions, but the superpositions have phase. And usually you see superpositions by seeing the phase vary. So it's generically seen in some interference pattern that you set up. And there was a tiny little bit of evidence of interference. So it was a sign that there was a bit of coherence, which persisted over very short times. Well, short compared with what? Well, not compared with, you know, the inflation period of the Big Bang, but it's on the scale of less than a nanosecond, which is about as short as you could measure in these kind of condensed matter experiments, these sort of solid state settings. So, so there was a little bit of coherence. And I mean, it was not that it was dismissed. It was, you know, it was in a prominent publication and very widely discussed. Wow, it's amazing that these dirty structures, and I'll show you how dirty they look in a moment, can show anything like clean quantum coherence. So that motivated other researchers to look, and this was a big breakthrough about 10 years ago. Now I finally show a picture of what these things typically look like. I mean, they're not very exciting. They're just, you know, well, I mean, it depends on your point of view. They're actually very exciting for some of us. But, you know, you go in the fabrication lab and you evaporate aluminum this way and you evaporate it that way, and, you know, you try to keep it a bit clean. This is not really that small. Here's a 1 micron scale bar. This is a lot of, the black stuff is just some insulating substrate, supposedly doing nothing, but in fact, over the years we found that it was doing stuff, mostly bad. But there's some substrate, you evaporate aluminum on it, and you arrange places where they overlap so that Josephson junctions are formed. Now, you can tell from the title and the data that I've shown from this paper from the group in Paris that they really did take a big jump in this sort of quantum behavior of this. They did it actually by making this structure bigger and more complicated than any of the previous experiments. So that sounds like the wrong direction. Big stuff isn't quantum. You know, it's small stuff that's quantum. But the message is big can be better if it allows you to implement some design ideas. You know, this actually has a bilateral symmetry, and that permitted this to be insensitive to certain forms of noise that would disturb these quantum phases. So it has not one Josephson junction, but three, and they're in particular ratios. There's one big, two small. There are various capacitors. There are places where you can apply magnetic fluxes. And then there are all sorts of very electrical-looking things, voltage sources, current biases, amplifiers. So despite all this very classical-sounding stuff right in the midst of the experiment, you nevertheless achieved something that, for all appearances, was indeed a quantum two-level system. And that they dubbed it quantronium, like a new element of the periodic table. It's not very unique in the sense that, you've changed the parameters a little bit and you have a new, quote, quantronium. But this particular quantronium had two energy levels separated by that many megahertz, so 16.4095 gigahertz. So a nice, convenient microwave frequency. And so they could illuminate this structure with microwave radiation at exactly that frequency and observe this interference pattern. And that did indeed prove, or was constituted as good a proof as you can make, as told to us by Norman Ramsey, basically, that this is the kind of temporal interferometry that you can do to prove that systems have two-level quantum coherence, and by measuring things about this, you measure how persistent this coherence is, and the scale is now, a good fraction of a microsecond. So this was about a factor of 100 jump in how coherent the system was compared with the work of 2 years earlier. This, of course, this was still, not extremely interesting from the point of view of like atomic physics. There are areas where you see routinely much more coherent two-level systems than this. But to make it in such a manufactured system, and you can take chips and laying it out, as I will dream about near the end of this lecture. And there was a lot of learning. There's a lot of details here that I could talk about. The data, the fluctuations of the data are not very, quote, statistical, and it was clear that they're struggling with various kinds of noise, so-called one-ref noise, where the parameters of the system vary slightly in time, and this was a real beast that they had to work very hard to control. Another problem is that the so-called fringe visibility, when you have really good interference and you have an interference pattern, the maximum to minimum should vary by 100%. This only varied by about 10%. So it was still not clearly imperfect in several different ways. But that got people thinking, we too can design other kinds of electrical structures with its own sort of energy potential surface and try out our own Schrodinger equations. And that turned out to work. I think I'll sort of skip these things in the interest of time to continue with the sort of experimental story. So there's another group at Yale University that achieved further remarkable things with this. Initially, not by changing this structure. This was actually back to the Nakamura structure, the one that had barely any coherence. But what they did was surround it by another electrical structure of many millimeter scale, this big or something, which is in fact a kind of transmission line. This meandering of this line is just for convenience, just to make it a little more compact. It's conceptually just a one-dimensional structure. So it is in fact just a transmission structure, but it's one with breaks here and here, so that it actually constituted a cavity for microwave radiation. So it's without the breaks, it's something that just carries microwave radiation like a coaxial cable. But by putting breaks at two places, they're like putting mirrors in, so that radiation will be trapped in here, or particular wavelengths. And so now their initial understanding was that this served mostly as a filter. That is, it was clear from other arguments that a lot of the problems with these qubits were just because there was a lot of electrical noise coming from the outside world. And these cavities have the property that if radiation comes in and it's not matching any of the resonant modes of this cavity, it just gets reflected back. So it's at least it serves as a good filter. And indeed, it did an excellent job of it in the sense that it immediately boosted this visibility from 10% up to 100% immediately. Well, this was 2 years later. And greatly improved the coherence of this simple structure. That is, this is, again, a significant fraction of a microsecond, which had already been achieved in Paris, but with a much more complex qubit, so to speak, with a much more complex Josephson Junction structure. Now, it was quite rapidly realized that, in fact, this is not merely functioning as a filter, but it's really a part of the quantum physics experiment itself, in the sense that the photons in here are also perfectly good quantum mechanical things. And the quantum state with one photon in that cavity, or two photons, are really good, distinct quantum states with excellent quantum coherence properties themselves. So, and in fact, this launched the subject, I didn't put it on the slide, but nowadays this is called a branch of quantum electrodynamics. It's called circuit quantum electrodynamics. And it has rapidly approached the Cape, or has, in the last few years, really replicated many, many things that were done in optics, in laser science, basically, in seeing the quantum properties of light, but just translated 4 or 5 orders of magnitude down in frequency. But the physics works very, very well, in fact, at these frequencies. And that will be a part of the story that I further tell. So you've got very much improved qubits, still not sort of atomic physics quality, but I'll come to the point of how good they ought to be, how good they need to be in a couple of minutes. So you've got that, and also this sort of complementary quantum system of equally good, or actually better quantum coherence, formed by these mirror structures. And mostly the story was, usually you make it worse. And I mean, this is generically true in material studies, that you'd have to work a long time, indeed, to see things that are better. Now we actually have seen a few materials that actually do, that are somewhat superior to the basic elemental metals like aluminum in their quantum properties. So this is something that it goes along also, but in fact, most of the achievements that have been made up till now, anyway, most of the milestones that have been achieved have been really with thinking hard about device structures rather than working hard on the materials. That might change as time goes on. Now, there was also a group where I was working until a few years ago at IBM that was working on these things, working on different device structures. This is another kind of qubit, 3 Josephson junctions with some extra capacitance. And now the qubit itself is getting to be many, many microns in size. So in fact, generally it was found making them bigger was better. So we and many other groups sort of put another order of magnitude or so in improvements in the basic quantum coherence that was seen. Well, a point we're starting to make is that can this be seen in every sample reliably? And the answer was indeed turning out to be yes. And another aspect of this work was that indeed the materials are messy, and that a lot of why the coherence isn't longer is because the substrate is lossy. There's regular so-called dielectric loss in substrate. So then people started working hard on that. Now, rather than tell the story, I told the story of several of these points. Now, what are these points? So this is my kind of Moore's law of this particular subject of coherence in superconducting qubits. So what's plotted on this axis is just one single figure of merit, which is how long, how persistent is the quantum coherence of these two-level systems. And so we went from barely observable to a big jump, Paris experiment, and one of these Yale experiment, IBM experiment, actually a whole lot of experiments. There are many, many groups that are innovating in this and just trying different things, and there's been pretty steady improvement. So the coherence has grown. Even the reproducible coherence has also grown. And then there's the rest of my lecture will be somewhat motivated by the fact that there's a line here. So this thing has grown. How far does it need to grow? Well, that depends on what you're doing. You know, if you're a, I'll say, metrologist, if mainly you're interested in, you know, achieving the most precise quantum behavior, and therefore needing to add more decimal places to look for new kinds of physics, then there's no limit. You want to just keep going as far as you can and start seeing, you know, what changes. And in fact, there is a sign. Well, I'm a little ahead of myself, but I mean, I glossed over much of the story of, well, what's superconductivity have to do with all this? And it is based on sort of Bardeen, Cooper, Schrieffer kinds of arguments. And at some point, did some of that go wrong? You know? And there are arguments that the physics of so-called quasi-particles, of unpaired, remember, superconductivity goes via Cooper pairing. Now, you often have stray particles that are not paired. And will they cause trouble? And yes, there's arguments that another couple of orders of magnitude up here, that they'll really put a wall. They'll stop you from getting better, and you have to really work a lot harder at the physics. But this stop line has nothing to do with that. This is, comes from a different set of arguments, which in fact comes right straight from the computer science side. They have nothing to do with physics. They just ask the question, how well do you have to do a Toffoli gate in order to successfully compute? Now, a Toffoli gate sounds like a totally discrete thing. You know, it has a truth table, and what does it mean for a truth table to be imperfect? But remember, now we're talking about a Toffoli with superpositions, and so you can ask, does the Toffoli actually do its thing properly and preserve superpositions properly? And that's more of a kind of analog thing. But nevertheless, one can prove, and I'll give you one sentence that covers, another 10 years of work and 3 lectures worth of information, that there is there's a possibility of error correcting faulty quantum logic circuits, and that there's a certain error threshold. It says that if the errors aren't too bad, that the error correction procedures can keep up with the accumulation of errors, and you can still get reliable computation. And there's a certain threshold, and with a bunch of assumptions, it's crudely here. So it says that's the sort of goal, is to get that much quantum coherence. It makes assumptions like that you can cause gates to happen. An important parameter is how long does the Toffoli gate take to occur. And the assumption is some number of nanoseconds, and that depends on the sort of microwave physics of these things. Now, this is actually a pretty fuzzy line. I mean, it depends on many, many assumptions. And in fact, it's the kind of thing where you really want to be far in excess of it. So the fact that there's one data point here from Will Oliver in the year 2010 of his flux qubit that happened to have 23 microsecond coherence. I haven't said this word, but we're up at many microseconds now, another couple of orders of magnitude beyond what I'd shown. If this Moore's law stops there, that's not such good news. But that's only data up to 2010, so if you look at the next couple of years of data, the news is good. But in fact, there's been enough, I've added 2 more orders of magnitude to this semi-log graph paper. And so a bunch of new points up to around 150 microseconds. So it seems like this stop line, well, I mean, it wasn't a physics stop line, and it was clear that the physics was quite capable of blasting through that. These are now experiments where if the experimentalist bothered to show a fringe pattern, it would look like, a textbook cosine wave, waving on and on and on and on. And that's the way it should be. And that's the way it is in precision atomic physics, or ion trap physics experiments as well. But that gets very boring to actually look at a Ramsey fringe. Because to the eye, you can't see any imperfections. These are all, well, from various laboratories. They all involve a particular trick, which I don't have really the slide that I meant to have here, but it's kind of a long ago art. Sorry, this is the sort of psychedelic version. I have a less psychedelic version of it, but comes from finite element modeling that long ago in microwave science, it was understood that you could also make good cavities, not with this sort of strip line method, but with just, two halves of a box put together. And that actually gives superior coherence than these evaporated, fabricated strip lines. I won't tell this story so much, but it at least showed, what it really showed was that none of these points are fundamental. There are no, like the Josephson Junction physics, there's no sign of any fundamental limit from the point of view of Josephson tunneling, that there's any hindrance on coherence, that it's all extrinsic to the basic superconducting device physics. Furthermore, this is sort of the last device fact that I'm going to mention, that these cavities, besides being good filters and having photons in them, actually provide sort of communications bus between qubits. So this is an experiment. Now, of course, people have been trying to do more than one qubit for a while, but this was a particularly important milestone in that it's an experiment where there's a cavity and there's a qubit here, and a few millimeters away there's a qubit here. And what they were able to do, the presence of this cavity mode, or a cavity mode, provides a coherent coupling mechanism between these two qubits, a few millimeters apart. And so you can run a particular protocol, that is, you apply the right bursts of microwave radiation to this structure. And what you will enact is not a Toffoli gate, but actually a sort of 2-bit version of a Toffoli gate, so-called control not gate. And that means various things. It means you can to good reliability, entangle these two things that are many millimeters apart. You easily violate Bell's inequalities, and all sorts of fundamental things are easily demonstrated in this experiment. They they decide to run a quantum algorithm. You can't do much algorithmic things with 2 qubits, but they ran the so-called Grover algorithm, and it worked out pretty well. Actually, the thing that I focused on, which you had to go back and dig into the supplemental material of this Nature article, is that the actual error or reliability of the 2 qubit gates that were in the heart of this algorithm were something like 90%. So that's pretty good, but it's not, it's not as good as you need, it turns out. The errors are partly due to this decoherence, but they're also due to the fact that the qubits are being controlled by this fairly complex shaped waveforms, and other things can go wrong. So, in fact, what we're shooting for, viewed this way, is what's this fidelity, or 1 minus this is an error rate for the operation of a 2 qubit gate. This has to get down to about 1%. That is to say, this number has to get up to about 99%. Now, I'll tell you in a moment where that's headed. But okay, what would you do if you had 99%? Could you build a computer? And well, yes. I say yes anyway. And we may still be a while before we could do this. Because of course, a computer means more than 1 qubit, more than 2 qubits, actually a lot of qubits. If you run Shor's algorithm and you're serious about it, you want 1 million qubits. Now, 1 million bits is no big deal. I'm putting my hand on gazillions of bits. I'm not sure which billion I'm talking about, but it's surely more than 1 million. So, but we need 1 million of these special things, and how could we get them? So this illustrates a possible solution, and it's sort of surprising that it's this simple in a way, that you just make a bathroom tiling out of the structures that people have made so far. So here's a cartoon, which is just, these light bars are these bus resonators, these cavities. And I've made qubits be just green dots, so it's very schematic. And each bus has 4 qubits sort of attached to it. So it means that 2 qubit gates can be done between any 2 of these 4, basically, in this structure locally. But then what you also do is each qubit is at the same time coupled to the edge of one cavity, but also at the end of another cavity. This is a trick that's quite doable in the microwave field and quite tricky in optics. It's very hard to make an atom, suspended in space at the same time coupled to 2 different optical cavities. But on a chip, it's not so bad. Actually, I mean, I say it because it's been done. That is, here's a sort of test structure from my old friends at IBM, where indeed, okay, here's 3 qubits, but it's 2 resonators, 2 cavities, one here and one here, and this qubit 1 is at the same time, as we say, dispersively coupled to both of those cavities. So it can participate via this cavity in gates, in entangling gates with this qubit, and via this cavity with entangling gates with this qubit. So now, why can it be so simple? I mean, computer chips don't look this simple. They have a lot of, tailored logic. There's no periodic structure to a regular chip. And that's actually because the real control of what really happens can be from the outside world. That is, there are places here where signals have to go on and off this chip. And all the complexity is encoded in the structure of those signals. And it turns out a regular periodic connected structure, but it must be in 2D. And there's some real, basically sort of quantum statistical mechanics behind that, of why 2D is really necessary and 1D structures are not sufficient. So this is now gotten into the minds of the people who work on this, that and the group at IBM is indeed interested, has, you might say, this picture as a milestone. I mean, I'm thinking government sponsors and people like that. Well, they've signed up to do an 8-qubit chunk of this. And if the sponsor's happy with that, they'll probably let them do 16 qubits or something like that. It becomes a big, big engineering problem. Lots of precision input-output microwave stuff going on that nobody's ever done before in any technology. So, and it's all at dilution refrigerator temperatures, by the way. So, in fact, there are a lot of fascinating physics questions connected just with that, about how you manage microwaves at the millikelvin temperatures. Not really quantum physics, just fun electromagnetics. This, well, I don't know if I'll tell this so much. This tells the reason why this is an error correction code. It turns out that the simplest error correction codes involve doing things with 4 qubits at a time. And, well, it's not necessary for me to explain this. And there's also a whole, you might say, science fiction behind, or there's a whole literature, which you can read in regular old physical review, where people are assuming, okay, suppose I have hundreds of qubits in a layout, what do I do with them? Maybe this is an interesting part of the story, that what you do with them is you make particular kinds of multi-qubit entangled states, or at least that's a way of, that's an equivalent language for the quantum error correction codes. But you leave patches of the qubits unentangled. So you make holes in which entanglement is not established. And then it's the dragging around of these holes. There are protocols for moving these holes around. And then by making the right space-time patterns of holes grading around each other, this at the moment is considered the most promising route to the sort of large-scale problem. So it is, in the end, a kind of topological quantum computing, if you've heard that buzzword. This has been very extensive. This has been very extensively simulated. There's Monte Carlo stuff that says that indeed the error rate, as measured by how good the 2-qubit gates need to be, is this number. So 1 minus that is this fidelity, 99.2% or something like that, is where this whole science fiction starts to work. So I think I'm basically done. Well, no, I will say that, so people are working quite hard, for example, at IBM, at seeing can they really get this, this fidelity up to 90%, 99%. And then, well, it's a complicated story. It gets hard to measure, or it gets trickier to measure, I should say. I don't know how impossible it's, or I don't think it's going to be impossible, but it requires sort of a new sort of precision mindset, which is being learned. And so the best numbers now are, this is sort of the relevant column, is sort of the 96% level. It's not actually so clear how hard that last few percent are going to be, whether it's going to be really, really tough, or whether they'll also sail through that number. I do not want to predict. I mean, actually, the last 6 months has not been so promising. There have been a lot of great ideas for making this number bigger, and they do an experiment, and it's not bigger. So, but that's just reporting things, you know, what's happening from month to month. This picture shows that there is even a possible way of making these quote 2D layouts with these traditional cavities. These are these cavities where you make two halves of a box and you just put them together. You have a cavity inside. So this is showing such a structure which has two cavities next to each other, two different slots. So I like to think of it, so what you're shooting for is sort of the waffle iron of cavities, you know, a whole array of cavities made out of two solid plates. And that's pretty much semi-seriously what these experiments are doing. This is not only from IBM, there are probably 4 different groups that are trying structures of that sort. So there we are. So I'm back to the beginning. Well, we got a big boost last year when this subject was honored by the Nobel Prize. And this phrase is measuring and manipulating individual quantum systems, which was honored here, is indeed the theme that I'm talking about. These guys did it in optical physics and in atomic physics, and well, we're trying to catch up and do it in solid state physics, but not only with, well, not just one individual quantum system, but lots and lots of individual quantum systems all working in concert. I think it's still going to take some time. But every 5 years has seen a lot of big progress. So I wouldn't bet against it. That's all. Thank you very much.
Why would it take so many qubits? I mean, you said 1 million. It seems like already 100 is a large number. Is it because of the coherence?
Oh yeah. Well, all I meant was it's not a large number if you're trying to factor a 1,000-digit number, and you need some like n-cubed scaling. I mean, there's several reasons why you need quite a few more qubits than there are bits to represent the numbers to be factored. Okay, but now the whole question is, I mean, yes, obviously, you know, the physics has to work at 10 qubits or 20 qubits or something like that. The buzzword is scalability. But you know, it's one thing to set up an experiment with literally 2 qubits or maybe 3 qubits and show that you can get a good gate between these. It's quite another to have an even more complex structure. And oh, by the way, you'd like to do them simultaneously, you know, between qubit 1 and qubit 2, and also between qubit 9 and qubit 10. And will you be able to preserve the fidelity that you know physics permits? I don't know.
So if you had perfect fidelity, you could have fewer qubits, I assume you would.
Yes, but who knows what perfect fidelity means?
More questions? So I saw this really sexy video on the internet of Google and NASA buying this like D-Wave
Oh, yeah.
quantum computer block. So is that not actually a quantum computer?
Not a quantum computer, yeah, amazingly. It is a superconducting, it is a Josephson Junction computer. Okay, that's a whole other story. But the D-Wave company made a decision quite some time ago to pursue quote, low frequency control. This is all, quote, high frequency control. So it's a different style of experimental attack on these Josephson qubits. And they also, because of what in my opinion is incorrect reading of theoretical ideas, they decided they didn't have to care about coherence. And that was because they're basing their approach on what's called ground state computing. So I mean, it is a physics-based approach that you stay in the ground state of some quantum many-body system, and that you say, oh, but that has entanglement. And they reasoned that, oh, and that entanglement wouldn't be very sensitive to noise, and that's where they're wrong. Now, they are mostly selling what they do as not quantum computing, that they merely have a sort of special purpose engine that does certain optimizations better in a way that doesn't depend on quantum coherence. But it's better in a sort of an ordinary level, that it's not sort of exponentially less resources, but maybe better, I mean, not proven at all at the moment to be better in any respect, but they hope it's sort of better. Okay, so that's my 3-minute reading of D-Wave. Very sexy, by the way.
What were the sizes of those last diagrams you showed? Of the, say like the waffle sizes, and like is there a lower bound on the size of the qubits?
Oh, you mean
Like the
this
physical
bathroom,
size.
this bathroom tiling thing?
Yes.
Oh, okay. Well, that's a good question because, of course, I'm a theorist. I can make any cartoons I want, but I mean, well, where's the scale bar here? This is indeed millimeters. So, so the first generation scale of this. Sorry, I'm moving around here. There it is. First generation thing scale of this is so this is several centimeters across. Now, if you do your arithmetic and you figure out can I get a million qubits at that pitch, it's kind of hard. There is indeed a whole other technical pursuit, like John Martinez is pretty big on this, of indeed making these things smaller. And because when you need sort of single mode resonators, and this is a very uncompact way of making them. This sort of straight line resonators is not at all a way of making something that resonates that's small. You can use sort of lump element ideas, but still basic electromagnetics for making them smaller, making the qubits smaller. I don't know. I mean, we've discussed this. 100 microns for this pitch seems sort of a reasonable goal. But it's actually going to be hard to kind of reminiaturize this. It'll never be small compared with CMOS, would be my guess, because, well, the scales, the relevant length scales of microscopic superconductivity will preclude it, if nothing else.
So right now, is the bound the bits or is the bound the microwave manipulation?
Oh, they're both really hard. I don't know. I mean, scrunching them down, that's one, specific technical problem. Managing inflows and outflows of microwave radiation in this very high Q system, I mean, just as a classical thing, it has things ringing all over the place, and you have to, not have crosstalk between things where there's lots of energy storage elements waiting to store and re-emit energy. So it's quite an amazingly challenging electromagnetics problem.
Your diagram at the beginning, with setting up the logic of this, specifically the logic gates and how you would pass it a superposition state. That works fine with a simple, 1-0 spin up, spin down system, but it seems like that logic would extend in some way to a system with more possible quantum states, which would allow computing using non-binary logic. Is anyone working on that? And is that of any value?
There's a lot of theory study of that. And there is in the literature, there are Q trits and Q quartz, and I don't know if the words have gone beyond that, but yes, and there are schemes worked out involving more level systems, even so-called quote continuous variable things, where indeed it's sort of the quadratures of the electromagnetic field, where the formal size of the Hilbert space is infinity. And some of them may work. It actually seems like going to a 4-level system is not such a spectacularly good idea. I mean, sort of for the same reason that computer logic works better, really 2-level, that you mostly don't even want a 3rd level.
Actually, push why does computer logic work better at TwoLevel?
At two levels, that's what I'm saying, yeah. But,
Why?
Oh, you're saying why? Somehow it's better that the component parts be as simple as possible. I mean, to me, the good historic illustration is up until the time of Turing, computing machines, which were made out of gears and cranks and things like that, were done in base 10. And that was really a stupid idea. Because the machine, the kind of Babbage-like machine is way, way more complicated when you're having to do things with base 10, 10-level objects than 2-level objects.
I see that. Makes sense. It does seem strange, though. I mean, I feel it seems intuitive to me, and I may just be adding from intuition here, but it seems like you would get more power per space if you were working with a more complex system.
I mean, the experience is, which is only experience, it may get changed, is that the added sort of bang per elementary object is more than nullified by the more complex control and also more complex noise features. And that's actually perhaps the even worse thing that multi-level systems bring in.
All right.
Let me propose to thank David again. He'll be around today as well as tomorrow, but very busy tomorrow, so you can continue this discussion after talking after lunch.
Guys, don't forget to hand in your homework.